Is it okay?
Yes, we see them.
Okay, so thank you. I will reduce that. Okay, so good afternoon, everybody. I'm Denis Mourard from Observatoire de la Côte d'Azur, and I will give you some news about the first light of CHARA SPICA, the integration and commissioning that is ongoing. So this program has been funded by many support from CNRS, Observatoire de la Côte d'Azur, University Côte d'Azur, the Région Sud, the Aarhus University, the CHARA, and more recently from the ERC. So in a nutshell, SPICA is first H-band 60 ABCD fringe sensor aiming at performing group delay and phase delay tracking of the fringes. Stefan already speak about that, and I will give you more detail on that. And it's an all-in-one 60 fibroid combiner working from 600 to 900 nanometer with free dispersion, a low resolution at 140, which is really dedicated for sensitivity and having something like 50 or 60 spectral channel of 5 nanometer covering the total spectral band in the visible, and two other medium and high resolution mode, more dedicated to the study, the kinematics of an environment. So in this table, we have some computation about the limiting magnitude, estimating as a function of the V square for a signal to noise ratio of 10 in 10 minutes of integration, and for one spectral channel. And for the differential visibility that we can compute also due to the spectral dispersion, we have also this number. So this SNR calculation is based on the FRIEND experiment published by Marc-Antoine Martineau a few years ago. Some hypotheses on the adaptive optic stress ratio of CHARA and the SPICA estimation we have in the instrument. So one thing that is, of course, really critical is the stress ratio of the adaptive optics. It was expected to be, it is expected to be something like 20-25% in the visible, but you can see that if we go below that, trend of 5% in bad condition or bad optimization of the hour loop, then we will lose typically 2 magnitude in the sensitivity. So now I will give you a tour of SPICA. SPICA is now this two big table installed at the place where Vega was, and you can see here the 6 entrance for the 6 beam coming from CHARA, and this part here is the spectrograph on a separated table, and the two tables are linked through single mode fibers. So here is the detail of the spectrograph table. You can see at the bottom here the injection system and the fiber coming to the V groove. And what we see here mainly is you can see two optics that are a little bit in blue here because of the reflection of two cylindrical lenses sending the interferometric channel through the dispersion system that is here, and you can see a detail of the dispersion system on the right images. And after that to the camera and the detector that is in this box here. It's an Andor 888 detector. And there is a second tube here on top of the interferometric channel, which is the photometric channel, where we do not make the anamorphosis of the beam, but we just transfer the image and pupil plane, so that on the detector, we have the equivalent of the dispersed image plane for the interferometric channel and the dispersed pupil plane, which is not really, but we can is the output of the V groove here of the system, and both images are going to the detector. On the dispersion system, we have the low dispersion system here made by the prism, a mirror plus a prism, and two gratings, and also a mirror for non-dispersion analysis. This is the general view of the injection table, where you have here the injection module at the bottom here, and the beams are coming from CHARA. We form an image plane at this location here, and then a refocalization, a recollimation in direction of the injection module. And here we have a field lens that permit to control the position of the pupil on the fast tilt mirror. You have a detail here of this system where you can see the fast tilt mirror here and the field lens. There is a recollimation by a f400 lens going to the injection module. Here we have beam splitter that take 10% of the light to send light into a second indoor camera for control of image and pupil by switching here a small lens that permit to visualize either the images or the pupil. In normal operation, we are looking at the 6 images and we are doing a fast control of the 6 tilt mirrors that are installed here. The injection module are refractive optics and installed on differential delay line for the control of the internal delay between the instrument and also for the co-phasing of instrument with the infrared instrument when we're using the longitudinal dispersion compensator. SPICA is also other pieces installed in different part of CHARA. We have here a second set of longitudinal dispersion compensator dedicated to the visible beam, and that comes on top of the main LDC installed in the common beams here. We have also the new visible, the Vis-fold optic that permit to send the light from the STS to SPICA in the visible, and here on the bottom you have the infrared mirror for the STS. We need also to use a periscope to go over the CHARA visible table, which is used for sending the reference laser beam into CHARA alignment. So this periscope is also equipped on each beam of atmospheric refraction compensator, which is needed for the sensitivity when looking at low elevation. And at the end, which is in fact at the entrance of the SPICA injection table, we have the polarization compensation system made of birefringent optics that you just tilt in order to change the thickness of the glass seen by the beam and compensate the birefringence of the fiber. So SPICA fringe tracker is as I told you, is a fiber integrated optics device that is working on edge-bound as a 60 ABCD combiner. It uses the Merckx injection system for the moment, the Merckx spectrograph, and the CERED1 detector. And we have, of course, developed the OPD controller as an adaptation of the gravity development made by Sylvestre Lacour. The goal for SPICA in the visible, in order to reach the science performance we want, is to allow the exposure time to go from 20 milliseconds in group delay to 200 milliseconds at least in the visible with a lambda over 8 stability. The goal would be to reach a few seconds of integration time if we are successful enough. So we have had the first light of this system with the EO-IO January 2020, just before the pandemic. We were only able at that time to make group delay tracking on 5 telescopes with the OPD controller. And now this program has taken a large delay because of the impossibility to travel during one year and a half. And we have developed a numerical simulator. This is the work mainly done by Cyril Panetier during his PhD, for analyzing the performance of on-sky result and on the test bed in Nice and in Mount Wilson, and also to develop the state machine of the fringe tracker for going from search mode to lock mode to track mode, and of course to make a very precise analysis of the fringe up that may generate some loss of visibility. So the goal here is to make more on-sky tests, including the new communication with the delay line control system. And we have now the third generation of the integrated optic chip that is ready in lab in Nice, that permit to correct some internal closure phase that were in the first generation of this combiner, and also to optimize the splitter function. So we hope to install it soon at CHARA. So some results from the first commissioning. So all alignment procedure up to the Fiber Explorer are well understood and stabilized. We have a tracking on image and pupil up to magnitude 8 with the current condition of adaptive optic and Strel, and with fast tilt correction at 100 Hz up to magnitude 7 or 50 Hz to magnitude 8. And this fast tracking system, as you can see on the upper image here, improve strongly the statistic of images with this is histogram of images as a function of the number of photons. This is for the four telescopes that we had last week and using the adaptive optics. So you see that the improvement in the potential injection is really important by this fast technique. We have made also some validation of the refraction and field rotation model based on actual observation, and this is shift and add long exposure of images with low elevation, large azimuth, and we clearly see strong elongation on the spots in white light. That will generate a loss of coupling, of course, in the fiber. So now we have a correct estimation of the field rotation and the orientation of the refraction, and we may be able now to drive the ADC correction. We are also doing with Pierre Geneslet an important simulation work using the YAO software to understand the current level of the Strel ratio on the AO system. And we have taken many data during this last month on telemetry data on the AO. And we are working on a possible new method for the reconstruction matrix that may improve the Strel in the visible. We still need to validate this approach and then discuss with the CHARA group, of course, for possible implementation and test. That's for the positive aspect. So we have more negative aspect. We have a big issue with our injection module. The injection module, the flux in the instrument itself, in the spectrograph, is very low, even with the 6 telescope simulator white light source. And for the moment, it prevents us to calibrate the birefringence of the fiber in the lab. And this poor injection is, in fact, closer to 1 or 2%, which is really, really bad. I don't speak about the effect of seeing, whereas 50% were expected, in fact. So we may have some focus or aberration issue in the system, and we have bring back one of the module in Nice to analyze what is the issue here. Otherwise, we have found, thanks to the 6 telescope simulator, all internal fringes, but we were not able for the moment to validate the first light on sky. So we have a few things that are ongoing with the upgrade of the V-groove to have a better alignment of the fiber, a change of the second cylindrical lens of the spectrograph to correct some chromatic aberration, and a change of the mirror of the periscope because the good mirror we have were broken during the transportation, unfortunately, and this permitting to have a very high definition in the 600-900 nanometer band. As said by Stefan, we have this new injection system for H-band that will probably be developed in 2022, and we are looking for the simultaneous operation of SPICA, Merckx, Mystic. We are also working on the final preparation of the list of targets for the survey, and working also on the validation of the data reduction software, which is a legacy from Fran and Matisse, and on the quality control software, which will in principle permit an automatic transfer function calibration and simple toy model fitting for quality control. rapidly, I would like to emphasize the very excellent collaboration we have the GNMC in order to develop the tools for SPICA around the main tools that the GNMC group has developed. The main goal, I will speak just after on that, is developing a large survey of stellar parameters, and we need an improved management of large list of targets. And we have developed a principle of a database with different applications connected to this database for managing large program, for the data feeding and a query system, for the night scheduling software. We have many more stars in the database than we will observe, but this software will permit to optimize the night by reducing the declination range, and also for the operation with the DRS and QCS, as I already speak. So this part are almost, this part is ready. This part is almost ready also. We are working on that for this summer, and probably also one thing that we wanted to analyze at the end is to use the principle of the A2P2 toy that is a tool that is developed by GNMC to communicate with the CHARA control system. So, yes.
You are at time.
Yes, I just have this slide on science, sorry. This is the main program we want to develop with the interferometric survey of stellar parameter, which is about exoplanet star, asteroseismic target, and calibration of surface brightness. This is closely related to the ESA Plateau mission and the Araucaria program. And there is a just recent job announcement on the AAS and my website. So thank you. I would like to thank all the people working with me on this program. And I'm sorry for being late, for being long.
Thank you, Denis. Do we have a quick question? Maybe we can squeeze one in.
There's one in the chat.
There's one in the chat. Oh, that chat.
Oh yes, there is a the fringe tracker we have developed is an ABCD, not an HFT concept. It's based on the ABCD in order to combine reliability and sensitivity. Yeah.
All right. Let's thank Denis again.